we figured out the torque on a square loop of wire. Let's do, just for fun, let's do an equilateral triangle loop with side A. Why not? So somehow, some equilateral triangle ended up sitting here like this. Side A, I won't write the A because there's a lot of stuff to draw. And it's sitting with a current going around it, current I, and it's in magnetic field pointing to the right, just like the square. Okay. I don't know if I need to draw that. Okay, so what is the force and what is the torque? So just like before, we'll give each side a number to help us keep up with what's going on. All right, so let's do them one at a time. What's the force on side 1? Well, let's see. So we got to think about what is L in this case. So the current's going around, so L is a vector pointing along this direction with magnitude A, right? Because the total length of that side is A. So the force is I L cross B, that's I. The magnitude of L is A, the magnitude of B is B. And then times the sine of the angle between them. Well, if this is 60 degrees of an equilateral triangle and that's 60, that would make that 60, which would make that 120. Okay? So if that's 60, this is 120, so we add the sine of 120. And then we need a direction. Let's see, so right-hand rule, if we have L going like this, then L crossed with B, this one has a force coming out. L cross B, the force is out. So I'll just draw the force vector F1 out of the board on that piece, right, F1. So I'll write out with a unit vector on it. We don't need to do X, Y, Z for this little problem. Okay, side 2. Side 2 has its L down here, like that. L is the same direction as B. The cross product, L cross B, is 0. So side 2 is 0. Side 3 is very similar to side 1. L goes up this way. Its magnitude is also A. So the force 3 is I, A, B, sine. It's the same angle between them, 120 degrees. And its direction, though, is in, right? Because if we have L cross B, the force 3 is in. So you can see, if we're pushing a force out evenly on this side and in evenly on that side, and there's no force down here, it's going to rotate, and it's going to rotate about an axis along the center. Since everything is nice and symmetric, we can just look at it and know the rotation axis. If this were all asymmetric, it'd be harder to figure out the rotation axis, but in this case, we know what it is. Okay, there's the forces. Now, let's think about the torque. So remember, torque was R cross F. Right? So let's see, what would torque be? Well, first let's finish this. This is square root of 3 over 2 I A B out. This is still 0, and this also square root of 3 over 2 is a sine of 120 I A B in. Okay, now we want to use that. So the torque is R cross F. Now remember, R is the vector from the rotation axis to the point that the force is applied. Okay, so that's actually changing here. This is the hard part of the problem. If you're talking about the force on this little piece, R is like that. If you're talking about the force on this piece, R is like that. On this piece up here, I'm going to start erasing things. There's R. So we're actually going to do a little shortcut in this problem because we have R changing. We're not going to do it in all of its detail. But I'm just going to tell you that if we were to add these up and do some sort of an integral, we'd find that this little piece, if we had the force per unit length, this little piece of force would apply no torque. This little piece of force would apply the maximum torque. that force times this full A over 2. Everything in between, it's just a linear increase from 0 to some maximum. So the average value, if you want to go with the average value, is the force times or cross with the radius crossed with the force at the center, at this point where we're at A over 2. See, here's A over 2 and A over 2. So at this point, A over 2, we want to use that value because that's the average value. So that is the radius vector we want to cross the entire force with because it's where it's the average. Okay, that's the little shortcut we're going to apply. Okay, so what is that radius vector? Well, this is a right triangle here. This is now 30 degrees. This is 90, and this is A over 2. So the sine of 30 is a half, so this is A over 4. Okay, so the R average vector we're going to use is A over 4 is the magnitude, and it's to the left. Okay, so we're going to cross that with the force, which is out of the board, and we know its magnitude. All right, so let's start multiplying the magnitudes of the two vectors. The magnitude of R, we just said, was A over 4. And then this one is the square root of 3 over 2iab times the sine of the angle between them. Well, that's 90 degrees, so the sine of 90 degrees is 1. These are actually normal vectors. This one is this way, this one is out. So if we have R cross F out, the torque is up. And that makes sense because it spins around the torque. So we don't have to add anything else. The torque is up. So it's A over 4 square root of 3 over 2 iab up. That's torque 1. Torque 2 is 0 because there's no force. Okay. Torque 3 ends up everything's the same. Same argument, everything works out the same. We're going to use the halfway point as the average radius. This radius here is R over 4. And it actually ends up in the same direction this time because radius has switched direction and the force has switched direction. So if we say R cross F, it's also up. So everything's the same. It's A over 4, square root of 3 over 2, IAB. Okay? So what's the total torque? Add up the torques. So if we add them up, let's see if I can get this reasonably correct here in my head. If we add these two up, then those 4s are going to become a 2. So it's A over 2 square root of 3 over 2 IAB up. We just added them. And now let's simplify it a little bit. And it becomes, let's see, I first, and then it's a square root of 3 over 4a squared. B up. So there is your torque. That looked like a lot of work to get something not so exciting. But let's realize a connection with the square. The square was I little a little b big B, right? And we said, hey, little a little b is the area. Interesting. Well, guess what the area of an equilateral triangle is? It's a square root of 3 over 4a squared. So when we did the triangle, we also got the same thing. It's the current times the area times the B field. What if we did a pentagon? Or I don't know, what is this? What am I making here? It's a hexagon. What if we did a hexagon? We could go through all kinds of horrible trig to do a hexagon. What would we get? We'd get the area here. Okay? It turns out that the torque, if you have a current loop and a magnetic field, is always basically equal to the current times the area times the B field. And you just have to get the direction right. So let's look at that a little bit more.